Ulf received his PhD in biochemistry from Lund University, Sweden, under the supervision of Professor Pettersson in 1991. He then moved into the field of theoretical chemistry at the same university as a postdoctoral fellow of Professor Björn Rose. He became a docent in 1996 and full professor in 2004. From 2001 to 2007, he had a senior research position at the Swedish Research Council. Ulf published over 300 papers. He studies the structure and function of proteins, in particular metalloproteins such as nitrogenase, particularly methane monooxygenase, lytic polysaccharide monooxygenase, superoxide dismutases, and hydrogenases. He has developed combined quantum mechanical and molecular mechanical methods for accurate treatment of environmental effects, for example, using accurate force fields with multiple expansion and anisotropic polarization, and combinations of QM, with free energy methods or experimental approaches, such as X-ray and neutron crystallography, cryogenic electron microscopy, NMR, and extended X-ray absorption fine structure spectroscopy. He also studies and develops methods to calculate ligand binding affinities, in particular PBSA, combined with Poisson-Boltzmann and solvent accessible surface area continuum solvation, and free energy simulations, as well as various combinations of and QM methods. So Ulf, the screen is yours.
Thank you very much for this very nice introduction. I want to thank the organizers, Paulina and Christophs, for this invitation, for giving me this opportunity to tell you about our research and about our quantum refinement method. Okay, so I will tell you about recent developments in quantum refinement, and that has been our subject for quite some time. The outline of the talk is that I first will tell you about the method, then I will show you some application, then I will tell you about the recent extension, especially extension to cryo-EM, and finally I will say a little bit out of the subject, tell you a little bit about our development of the FRAG-HAR method also. So our group is doing computational calculation, computational chemistry of preferably protein structures, and then we always need to start from a structure. And of course, we can decide if we want to use computational structures, which can be used directly for calculating, for example, energies, although they are not experimental structure and it might be a bit inaccurate. Or we can use experimental structures like, there are many different types of experimental structures nowadays, which are in some way the true structure, but there are problems with disorder dynamics and other things. And the bad thing is that you cannot directly calculate energy from them because there are uncertainty or small errors both in the experimental and the calculations. So what we found out is that every project we have, we start by re-optimizing a crystal structure. And then we asked ourselves, can we not do anything that is better than that? And then to understand what we need to do, we have to look a bit upon the crystal structures. How do you do crystal structure? You probably know most of this already. You have to get a crystal, of course, and then you collect the data. And the important thing for those that don't do structures is to know that the PDB files you find is not the experimental raw data, but they are the product of an involved process. So the raw data is essentially the structure factors you collect, and then by different methods you can get the experimental phase or some indication of the phase, and together with the phase then you can build the electron density map. And in this map you then build your model, your coordinates, your atoms. And then you have several steps of model building and then crystallographic refinement, where you try to optimize your model within this map. And we will deal mainly with this step of refinement. So the step of crystallographic refinement, you try to minimize the error between your experimental data and your current model. And you do that by minimizing probably something similar to the difference between the observed structure factors and structure factors calculated from your current model. And this is essentially the crystallographic R factor. You try to minimize that, but it has turned out that that is not enough. So when you do crystallographic refinement, you add a term which is some sort of empirical restraints, which in the language of computational chemistry is essentially a molecular mechanics energy function. So you will almost always use an energy function like this, one crystallographic term and one molecular mechanics term. And why do you do that? The reason for this is that the crystallographic raw data for most medium and low resolution structure is not accurate enough to exactly pinpoint where the atoms are. So in general, you could say that the experimental data gives you the general fold and the dihedrals of your structure, whereas the exact bond length and angles are given mainly by the molecular mechanics potential. So it ensures that you get chemically reasonable structure. But of course, that means that you also go a little bit away from the original crystal structure. So it means that you increase the crystallographic R factor. If you do it only locally, it's only a small difference. But if you do it for the whole protein, it's quite significant difference. But on the other hand, you get a structure that looks chemically reasonable and not just a mess of atoms with strange bond length. And from a computational chemistry point of view, there are several problems with this. One problem is that the molecular mechanics is not the most accurate computational method. It's fast and it's easy to understand and it's easy to manipulate. A second problem is, of course, that the results will depend on this molecular mechanics potential. So if you have a bad potential, you will get a bad structure. And if you have different molecular mechanics potential, you might get different structures, like shown in this figure. And the third problem, and perhaps the worst one, is that the quality of the crystal structure will be different in different parts of the structure, depending on the molecular mechanics potential. And in general, you have quite accurate molecular mechanics potential for amino acid, nucleic acid, things that you have accurate crystal structures of. Whereas for other things that are less common in crystal structure, like the substrates, inhibitors, drug candidates, metal sites, there you have much less experimental information and therefore less accurate molecular mechanics potentials. And the bad thing is, of course, that these hetero compounds, they are mainly found in the active site. So in the most interesting part of the crystal structure, there the accuracy might be worse. So already more than 20 years ago, we suggested how we can solve this problem by employing quantum chemistry instead of the molecular mechanics potential for a small but interesting part of the protein. So this is similar to what you do in standard computation chemistry with the QMM method, the combined quantum mechanical and molecular mechanics methods. You use quantum mechanics for small part and then molecular mechanics for the rest. And here we replace the empirical restraints with a QMMM energy function, which equivalently could be seen as a QMMM optimization with restraints toward the crystal structure. And then, of course, the question is, does this work? And to show it, it's not trivial because, as I said, the empirical potential will always move the structure a little bit away from the crystallographic raw data. So to prove that this works, we found out that we could use some protein where we have two different crystal structures, one at a medium resolution and one at a very high resolution. And then we can show that by using only the low resolution data, we can bring the results closer to the high resolution results. And we found this cytochrome C553 protein, which contains a metal site, which is of interest to us. It contains a heme group with an ion in the middle, and then one histidine and one methionine as the axial ligands. And then, as I said, we refined this structure using only the low resolution data and showed that we can bring it closer to the high resolution structure. And fortunately, there was quite a difference between the original low resolution structure and the high resolution structure, especially in this distance. And we could show that by our method, which we called ConcuMX, we could bring the structure much closer to the high resolution data without actually using the high resolution data. And we could also show that we improved the R factors very little because this is very locally in a big structure, but still we improved them. And the reason why we could do this is because the quantum chemical calculations already in vacuum gave very accurate results. And that's, of course, the basis of this method, that we know that the QM calculations are very accurate. So standard density functional theory typically give metal ligand bond lengths that are correct within 0.02 to 0.05 angstrom, which is actually better than standard medium resolution crystal structures. So that's the method. And then the question is, what can we use it for? And I will show you a few applications. So one thing we could do is to actually, or try to see what we actually don't see in the crystal structure. So try to deduce where are, for example, the electrons or the protons. One typical thing you could be interested of is the protonation state of metal-bound water or solvent ligands. So from computational studies, we know that there are quite a difference if you deprotonate the water molecules to OH ion. So if we know beforehand what this difference is, we could see which of the two structures fits the data without actually seeing if there are one or two protons. And to show that this works, we need a good test case, and one such case is alcohol dehydrogenase, the enzyme that converts alcohol to aldehyde, so boost to hangover. And this enzyme contains active site zinc ion with two cysteine ligands, one histidine ligand, and then a solvent molecule. And from kinetic studies, the pKa of this solvent molecule of water or alcohol is known, and it depends on which coenzyme is bound and if it's alcohol or water. And then we found out a crystal structure containing, in this case, NAD plus and alcohol. And from kinetic data, we know that the pKa of such a complex should be about 6. And the crystal structure was collected at 8. So that means that the ligand should be alkoxide, so deprotonated alcohol, rather alcohol. And then we see if we can reproduce this with our quantum refinement. And what we do then is to do quantum refinement with both alkoxide and with an alcohol, so with or without this hydrogen atom. And then we see which of the two fits the crystallographic raw data best. And we do that by looking at some different things. So here, the upper part of the table is the alcohol, the lower part is the alkoxide. And we can, for example, look at the R3 factor, and we can see that the R3 factor is always lower for the alkoxide than for the alcohol. We can look at the zinc-oxygen distance, so this distance, and see that for the alkoxide, it's always close to the ideal distance, so the vacuum QM calculation. They give almost exactly the same results, whereas for the alcohol, it's far from the ideal bond length, and it depends on the weight factor between the MM and QM energy function and the experimental energy function. So once again, this points towards the alkoxide. And finally, we can look at the strain energy, which is the QM energy of the quantum system. So this model, when optimized inside the protein, so with a quantum refinement, or optimized freely in gas phase. And once again, we can see that it's lower, so the structure is less strained by the crystallography for the alkoxide than for the alcohol. So all three criteria points out the alkoxide as the better one, and that's in complete accordance with the kinetic data. So we can actually deduce from the crystal structure that this contains alkoxide and not alcohol. And just then to check that this is not just a coincidence, we did another structure which is still an Nad+ complex, but now with a water molecule. And then the pKa should be 7.6. The structure is from 7 pH 7, so it should be mainly water. And once again, we do the calculations either with water or with OH. So water or OH. And we can see with the same criteria that now, in this case, the water fits the data much better. So the R3 factor is lower for water than for OH. The oxygen zinc distance, this distance here, is more similar to the vacuum structure for the water than for the OH group. So it's very much more similar. And the strain energy is lower for water than for OH. So again, all three criteria point out the correct protonation state. But then we try to do this also with another protein, which is manganese superoxide dismutase. It contains a manganese ion bound to 3 histidine ligands and 1 asper glue group, and then there is a solvent molecule. And this enzyme can either be in the oxidized manganese 3 state or the reduced manganese 2 state. And it was believed that manganese 3 would give a OH ion, whereas manganese 2 would give a water molecule. And we started from a 2 crystal structure, one reduced and one oxidized. And for the reduced, all results looked very good. We compared water against OH, and in all cases, so the R3 factor, the residue R factor, the manganese water distance, and the total difference between all the metal ligand distances, and also the strain energy, were always better for water than for OH. So for the reduced state, we can clearly say that it binds a water molecule. But then we started with the oxidized structure, or the structure that was said to be oxidized. And then we got problems, because for some criteria, we get water with a reduced manganese best. Some other criteria say reduced manganese with OH. And one criterion instead said that it was manganese 3 with OH. And first we thought this was a bad system, but then we found out that what's happened here is that when you beam X-ray on a crystal structure, then you release electrons, and electrons go wherever they can, and preferably to sites that can be reduced, for example, metal sites. So even if the structure was started at the oxidized state, so manganese 3 with OH, during data collection, it slowly changes to the reduced state with manganese 2 and water. And the crystal structure is then a mixture between these two states, and therefore we cannot say what it contains because it's a mixture. So the bad thing is that quantum refinement will have problems with this structure. The good message is that we can see that from the results. We can see that we get a mixture, that we don't get any clear results. So we can actually see if structures are photoreduced. Then we go to some other applications. So now we look at the protein called the particulate methane monooxygenase. Particulate says only that it's membrane bound. Methane monooxygenase says that it converts methane, oxidized methane, to methanol. And there are only two types of enzymes that can do this quite hard reaction. And the fact that the enzyme is membrane bound is very problematic experimentally because it's hard to make crystals of membrane bound protein, and therefore there are a big controversy regarding this enzyme. We don't know how many metals there are, we don't know which metals there are, and we don't even know where is the active site and how many metals do the active site contain. There are especially two groups, one saying that it's a trinuclear kappa site, another group saying that it's a mononuclear kappa site, and they are at different positions. When we did this study, there were only a few crystal structures, all of them at a low resolution. And in this structure, the putative active site at that time was a dicopper site, but the structure was totally crazy from an inorganic perspective. It looked like this in one subunit and like this in another subunit. And an inorganic chemist cannot recognize metal binding site here. So we thought that we could sort this out by quantum refinement. So we started to do this site with 2 copper ions, and we could get a little bit better, so at least the ligands point towards the metal, but it still has strange structure. We tried to add more water molecules to give it more ligands, but still we got only strange structure. And then at the end, we decided to use just 1 copper ion. And then suddenly we get something that looks like a normal kappa site, an almost square planar kappa site with 4 ligands, and the small positive density, which was interpreted as a second copper, we could model quite nicely with a water molecule instead. So we're quite confident that this is not a binuclear site, but a mononuclear kappa site, and that was later confirmed by other experimental methods. Then we turn to another enzyme we have done quite a lot on, that's nitrogenase. That's the enzyme, the only enzyme that can cleave the triple bond of N2 into 2 ammonia molecules. And it has one of the most complicated metal factors in nature. So it contains 1 molybdenum, 7 iron ions, 9 sulfide ions, 1 carbide ion, and then unusual homocitrate ligand. And just a few years ago, there was a new crystal structure of nitrogenase where they said that they could actually see reaction intermediates, because the problem with this enzyme is that we don't know where N2 binds. We have only structures of the resting state. But now in 2020, there was a structure said to contain N2. And the strange thing was that in one subunit, they saw 1 N2 molecule replacing a sulfide ion. And in the other subunit, they saw 2 N2 ions replacing the other 2 of these bridging sulfide ions, so these 2. But you can also see that the structure looks quite strange. The electron densities are very anisotropic, and the structure, which was at 1.8 angstrom, that's only in one direction, whereas in the other direction it's almost 1 angstrom worse. So we decided to see if this is really M2, because that would be sensational. But when we do quantum refinement, so we did quantum refinement with N2, and we could get a better structure with less anisotropy and less difference densities. It's not perfect, and we still have some positive difference density here. But if we then replaced the N2 ligand by the standard sulfide ligand, we get something that is much better, no difference density here, and a much better residue real space Z score, which is the criterion we're nowadays using. And that was one subunit. For the other subunit, it was essentially the same. We could reproduce the suggested structure, but we have lots of positive difference densities, bad Z scores. And if we replace it with the standard resting state with all sulfide ions intact, we get much better results. We still have a little bit of difference density here, so it's not fully perfect, but it's much better than the original suggestion. So in our hands, there are no evidence that there should be any M2 bound to the cluster. So that was some applications of this quantum refinement method. Now I will talk a little bit about extensions of the method. The program we are using, or have been using for the crystallography, that's the CNS program. And this program can equally well be used for neutron crystallography. So therefore we could quite easily do neutron quantum refinement also. We replace the X-ray term with a neutron term, or we could use both terms to do joint refinement. But we still have these quantum mechanical terms to replace the empirical restraints. And that works excellently. I will show you two structures we have done. One is with galectin-3, so that's a carbon hydrate binding to a lectin. And we didn't see much changes in the structure. It was mainly water molecules that changed their orientation when we do quantum refinement to improve the hydrogen bonds to the surroundings. Perhaps a little bit more interesting is the LPMO calculations of the lytic polysaccharide monoxonase structure. And this is the active site. It looks quite a lot like the PMMO site I showed you before. So with 3, or in this case 2, histidine ions, one of them binding with both the side chain and the amino terminal. And for this structure, there was a superoxide or peroxide structure, which by the crystallographer was suggested to show a doubly deprotonated amino terminal, so a NH minus group, whereas a more chemical interpretation would be NH2, so singly deprotonated and neutral. This is neutral, this is negatively charged. And you can see that this is quantum refinement of the neutron structure with NH2 or with NH, and we have much less difference density in the NH structure than in the NH2 structure than in the NH minus structure, as suggested by the crystallographers. So we can do neutron crystallography easily. We have done other extensions of the method. We have done NMR structures, which can also be done by a CNS. The N in CNS is NMR. And it's only that we replace the crystallographic restraints by instead NMR. restraints, and what you typically get is a number of different structures, or an ensemble of structures rather than one single structure. But in this case, you could describe metal sites, which normally are ignored in standard NMR structures. We showed also that we can do EXAFS, that is extended X-ray absorption fine structure. That's a totally different method. It's normally used just for metal sites in proteins, and you get very local information around the metals. So it was a little bit harder to implement it. We had to use other software, but we can add a EXAFS penalty term, which is typically chi-square term, to a QMM energy function. And then we can use it to determine what do we actually see in the protein, which is the best structural interpretation. So in this case, we look at lacase, where you have 3 nuclear kappa sites. So there is 1, 2, 3 kappa ions, each with 2 or 3 histidine ligands. And then there is a peroxy intermediate, which could either be O2, 2 minus in the middle of the cluster, or a peroxide ion at the side of the cluster. And we could show by this calculation that this one, the central binding, fits the experimental data much better than the peroxide structure. So what I want to concentrate a little bit on now is our latest development. So as I said before, the crystallography program we have used before is the CNS program that was very much used when we developed the quantum refinement method 20 years ago. But nowadays it has become more outdated and replaced by other programs. And for the QM calculations, we used TurboMole, which is a fast and good program, but unfortunately it became commercial. So it's not freely available to any user. And that's, of course, not so good. So for almost 10 years, we have struggled with implementing quantum refinement with Phoenix. And changing TurboMole to a freeware like Orca would take, or took, only 1 or 2 days to do, because that's easy to do. But to dig into the Phoenix program has been a pain. And it was not until we got a very skilled programmer in the group, Christopher, who finally managed to dig through all the labyrinth of Phoenix and actually made possible to do quantum refinement with Phoenix and Orca. And that opens immediately some new applications. We can do both reciprocal space and real space refinement, meaning that we can do X-ray, neutron, and cryo-EM refinement with the same program. And that's what I will talk about a little bit now, of some applications on cryo-EM structures. And then we go back to the PMMO, so the particulate methane monooxygenase, because recently there have been published 2 cryo-EM structure, or 2 groups have published structures. One is the same group that published all the crystal structures, that's the Rosenzweig group. They published 8 structures of different organisms and different lipid structures around it. They observed the same 3 mononuclear kappa sites as in the crystals. I will call them kappa A, B, and C. And nowadays they think it's not kappa B that we looked on before, but kappa C that is the active site. And then the other group is by Sunny Chan, who has always argued that the active site is a 3 nuclear kappa cluster. And they did 1 cryo-EM structure where they see the kappa A and B site. They don't see kappa C, which is Rosenzweig's active site, but instead they see what they call the kappa sponge with 3 kappa ions, 1 plus 2. And then they see 2 kappa ions in what they think is the active site, where they had expected 3 kappa ions. In refinement, we go back to PMMO, And there are two groups that recently have published cryo-EM structures for PMMO. That's the Rosenzweig group, who did the crystal structures, and they always see 3 copper sites there. The kappa B site we looked at before, kappa A, which has 2 histidines, and the kappa C, which they now believe is the active site. And then there is a Sanishan, oops, what happened here? Sorry. There, yeah. The Sanishan group, which always say that there are more kappa ions in this structure. They say that there are 8 kappa ions, including the kappa A and kappa B site, but not the kappa C site. And instead they see what they call the kappa sponge, which is 1 + 2 kappa ions. And then they see what they think is the active site, which should be 3 nuclear, but they see only 2 kappa ions. And then we will, let's see, next, yes. So we have done quantum refinement of all 3 of these structures with all kappa sites. And we look at the real space correlation coefficient and strain energies to decide which one is the best one. And we start with the uncontroversial site, that's the kappa A site. And I will look at 2 different structures. I look at Chan's structure. Yeah, so I should first say that this site has either 2 histidine ligands or 2 histidine ligands and a glutamine ligand. So in the Chan structure, there are only the 2 histidine ligands. The glutamine is 5 angstrom away. And quantum refinement doesn't do much to the structure. It shortens the distances a little bit, but the strain energy goes down a lot, but also the real space correlation coefficient goes down a little bit, which is sort of expected because we are adding some extra restraints on the structure. If we do the same thing with the Rosenzweig structure, the same thing happens. Nothing, the structure doesn't change very much, a little bit change in the distances. In this case, the real space correlation coefficient doesn't go down very much, but the strain energy improves a lot. Then we go to the more controversial sites. So the kappa B sites, which we looked at before, and the funny thing is that the Chan group, again, models it as a binuclear site, whereas Rosenzweig models it as a mononuclear site. And if we start with the mononuclear site in Rosenzweig's structure, not very much happens. The distances change a bit, and we get a slightly lower correlation coefficient and much improved strain energy. But if we look at the Chan structure, then they model it as binuclear with very strange geometries to the ligands. And here we have a large movement in the kappa ion. So the original structure is yellow, and then we have tried either kappa 1 or kappa 2. Kappa 1 is green, kappa 2 is magenta. And you can see that quite a lot of things happen. So you can see that in the original structure, there are totally crazy kappa nitrogen distances. And they, of course, improve if we do quantum refinement to more realistic distances. The correlation coefficient goes down, strain energy goes down, but not as much as for the other sites. And then we try to put in just 1 kappa ion, and then we get something that looks much better. It looks like a kappa site. We get reasonable distances, a slightly further lower correlation coefficient, and the normal strain energy. So we're quite sure that also the Chan structure is mononuclear. And what I show here is from a website called Check My Metal, which tells you if a metal is good, or metal geometry in a crystal structure is good or bad. So green is good, yellow is borderline, and red is bad. We can see that the original Chan interpretation contains some red fields and lots of yellow fields. So this web server says that it's quite bad. And that's what we see in our refinement also. Then we will do one more site. We will do one part of the copper sponge, which was only seen in the Shan structure. And it looks like this. It looks rather crazy because there is only one reasonable copper ligand, that's a carboxylate group. And there are arginine ligands, two arginine, one is here and one is there, which point their hydrogens towards the metals. But there is a small blob of density where they have built the metal. If we do quantum refinement on this, then the metal moves out of the blob and it goes towards the only reasonable ligand. I should say also that the Check My Metal says that this is a very poor site. And even if we put in, do quantum refinement with the metal, we still get very bad geometries because there are only one ligand and that's not reasonable. So then instead we try to put in a water molecule, and with the water molecule we get a very nice hydrogen bond network. The water molecule stays in the density and we get a rather good real space correlation coefficient and a normal strain energy. So we are quite certain that this site was incorrectly modeled as a metal. It's rather a water molecule. So that's some of our applications for the cryo-EM. Some conclusion is that it's a little bit harder than crystallography. One reason is that the resolution is unknown and it's different in different places in the structure. There is no model bias, so the map doesn't improve. If you improve the model, you have the map and you cannot change it. Of course, the restraints will always increase correlation coefficient, and that's the only quality measure we have. And it's well known that you need to heavily rely on restraints to get a good structure because the resolution is quite low. And of course, for the amino acid part, we have good restraints, but metals are not restrained at all, and therefore you can get strange structure for the metals. So our conclusion is that quantum refinement is actually the proper way to treat metal sites in cryo-EM structures. That's the only good method to get good structures of metals in a cryo-EM structure. And finally, I will say a few words about the Frag-Haar method, so the Hirschfeld atom refinement method. Now let's see there. So what I have done so far is to use quantum methods to improve the empirical restraints in crystal structures by QM calculations, and that's needed for low and medium resolution structures. What I will discuss now is the Haar method, so the Hirschfeld atom refinement, where you replace the atomic form factor, so you recalculate them from quantum mechanics and replace the independent atom model in the calculations instead. And this is useful only for very high resolution crystal structures. So we are at a totally different domain of structures now. And of course, as the structure becomes bigger, it becomes very time consuming, the standard form of Haar. So what we did a few years ago with Justin, we developed the Frag-Haar method, where you divide your molecule into fragments, overlapping fragments, and you calculate the structure factors or the form factors by quantum chemical calculations for each of these fragments, and then you tie them together. And we showed that for polypeptides, this worked excellently if you include hydrogen bond acceptors in the calculations. So then we can get very good bond lengths to the hydrogen atoms. And of course, I am more interested in proteins, so we wanted to develop a Frag-Haar method for the proteins, and that's what we have done recently to a big point with the help of Florian. So we have implemented Frag-Haar in the OLX2 software with the Nosferatu. method and QM with Orca as before. And by doing this, we can do FRAG-HAR calculations for entire proteins. So we have applied it to 2 proteins, crambin with 800 atoms at a very high resolution, and rubredoxan with more than 1,000 atoms, and a metal site at a slightly higher resolution. And this is just some pictures of what you can get. This is the metal site in the rubredoxin, where you have an ion bound to 4 cysteine groups in the protein. So that can be done now, although it's quite painful to do proteins in OLEX2. So the problem is not to do the QM calculations, the problem is to do the refinement for a full protein. So finally, I come to the conclusions. I hope I have convinced you that you can use quantum refinement, and it provides a good or ideal compromise between quantum chemical calculation and crystallography. You can use it to improve, and you can use it to interpret protein crystal structures. You can determine protonation state, oxidation state. You can do discrimination between different structural interpretations of the structure. And you can extend it to neutral crystallography, cryo-EM, and other methods. And I haven't shown you, but we can treat multiple conformation easily. And in the future, we want to use the electron density directly. We will want to combine quantum refinement with HAR method. We think that a very good application is time-resolved crystallography, where you always have mixtures of different states in the structure, and then you heavily rely on the empirical restraints. And of course, then quantum mechanics would be the better, especially as you often have strange states of your ligands or substrates or other things. And we want to do extend it to X-field data. We want to extend it to electron crystallography data. And finally, I want to thank all those who has developed different parts of this method. So all these, my previous and current students, and I also have lots of help from Esko, Derek, and Dylan. And finally, I want to thank these for computer time and this for money, and of course you for your kind attention. And sorry for the technical problems.
Thank you very much, Ulf.
Thank you very much, Ulf, for this really excellent lectures. And now it's time for comments and questions. I would say that our community is really fully aware of the importance of such approaches, and actually it's quite difficult to understand why they were waiting for such a long time. I mean, these methods are now being developed quite intensively, but say they could have been developed much earlier, but it wasn't the case. You were talking about structures. How, can you comment on any estimation of temperature factors, ADPs, on say?
So for the ADPs, I don't think quantum refinement can help much. We can do the standard B-factor refinement, but since we are replacing the empirical restraints, that shouldn't affect the B-factors very much. But of course, in the FRAG-HAR methods, we do B-factors, and they improve by the HAR method.
With this quantum refinement approach, and you restrain quantum calculations, you showed many structures. Can you comment on the resolution? For what kind of resolution it's still worth to apply it, or?
So I would say that it's, in principle, it's better the worse the resolution is, because the worse resolution you have, the more you have to rely on the restraints. And I would say that around 1 angstrom we start to see the systematic error or the DFT calculations. So below 1 angstrom, you actually do mostly bad things with the structure, because then the crystallographic data is better than the QM calculations.
Surprising. I thought you would need to go to much better resolution to see the discrepancies. But is there a lower end of resolution, like a limit? Like, let's say at some point, well, you see improvement in your strain energy, but you don't see any improvement in the fitting to the data because the data are so low resolution.
I would say that at low resolution, you rely heavily on your starting structure. So how do you interpret?
Okay.
Of course, we cannot, we can improve the structure, but it depends a lot on which ligands do you give to the metal. We cannot invent new ligands. So then you're, it's a matter of your fantasy. How should you build? When you don't have any experimental information, then you need to guess. And then it depends on what you guess.
If you increase the level of theoretical approaches, how much does this influence on the final results? If you go to some very much advanced methods.
Yeah, so that of course depends on the resolution. So at low and medium resolution, the final structure will reflect your QM method. So you will get the accuracy you have in QM method. If you go to very high resolution, then you will get something that is a compromise between the QM and the experimental data. So normally for standard protein crystal structure, DFT is a good method. If you want to do very high resolution structures, it might be that you need a better method.
How about computing time? What's your...
It takes the same time as a standard quantum mechanical or QMMM geometry optimization. So the things I have shown you today, you can do in 1 day about on a standard computer. But that's of course much longer than what you do with the standard crystallographic refinement, which you do in a few minutes.
Yeah, but you compute the restraints once, or you repeat computing it after each cycle of refinement?
We essentially do a geometry optimization. So you calculate new forces every time, every iteration, and you do it iteratively. So it is a standard QM geometry optimization with some experimental data added to the forces. So you will feel at home if you're a computational chemist, because it looks like a standard method. With Phoenix, we do it a little bit differently, because there we let Phoenix do the geometry optimization. So then it looks more like a standard Phoenix refinement.
Yeah, but that's only the changing the software, but not the approach, right? So
no,
it's
exactly.
still. So it looks like more that you are doing geometry optimization with some restraints from experiment, rather the other way around.
You can see it that way. You can see it from both ways. So either QMMM method with restraints to the crystallography, or a crystallographic refinement where you replace the MM calculations with QMMM calculations. That's equivalent ways to look upon it.
It's exactly in line with definition of quantum crystallography, if there is any fully acceptable.
Yeah.
Yeah, very, very interesting, really. Thank you very much, Ulf, for this lecture.